It looked like a monster. 6 axles, a long hood stretching nearly 70 feet, and inside that frame was something American railroading had never seen before: a 20-cylinder diesel engine producing 3,600 horsepower. The EMD SD45, introduced in 1965, represented the pinnacle of the horsepower race that defined late 1960s railroading. But power always comes at a price, and the SD45's V20 engine, the 2645E3, pushed the boundaries of diesel locomotive technology in ways that would reveal fundamental limits. This wasn't just about adding more cylinders. It was about harmonics, thermal stress, crankshaft dynamics, and the complex physics that govern large reciprocating engines. The SD45 sold well initially. Railroads ordered over 1,200 units between 1965 and 1971. Southern Pacific alone purchased 355. Santa Fe bought 93. Burlington Northern operated large fleets. These machines dominated fast freight service and mountain operations through the late 60s and early 70s. Yet, within a decade, many railroads were rebuilding them, converting them, or retiring them early. The V20 engine that promised so much had proven to be mechanically problematic in ways that EMD hadn't fully anticipated. To understand why requires looking at the engineering decisions that created this locomotive and the physical realities those decisions encountered. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The mid-1960s railroad industry faced a fundamental operational challenge: moving more freight with fewer locomotives. Labor agreements made crew costs a major expense. Every locomotive eliminated from a consist saved money. Every unit of horsepower added meant faster schedules and heavier trains. General Electric had entered the heavy road locomotive market aggressively. Their U25B, introduced in 1959, proved reliable enough to break EMD's near monopoly. By 1965, GE offered the U28C at 2,800 horsepower and was developing the U30C at 3,000 horsepower. Alco, though struggling financially, had introduced the Century Series with comparable outputs. EMD needed to respond decisively. Their SD40, introduced in 1966, offered 3,000 horsepower from a 16-cylinder 645E3 engine. But railroad purchasing departments wanted more. 3,000 horsepower wasn't enough of a leap to justify wholesale fleet replacement. Marketing studies indicated that 3,600 horsepower represented a threshold that would make railroads commit to large orders. The problem was thermal and mechanical limits. EMD's 645 engine family used a 9 1/16" bore and a 10-inch stroke. Each cylinder displaced 645 cubic inches, hence the designation. At 3,000 horsepower, the 16-cylinder configuration was already operating near the limit of what could be reliably sustained in continuous service. Simply, increasing boost pressure or advancing injection timing risked piston failure, excessive cylinder temperatures, and reduced component life. EMD's engineers calculated that pushing a V20 beyond 3,000 horsepower would create warranty exposure they couldn't accept. The solution was to add displacement, 20 cylinders instead of 16. This allowed the same mean effective pressure per cylinder while increasing total output. In theory, it was mechanically sound. Each cylinder wouldn't work harder. There would simply be more of them. What this approach didn't fully account for was the systemic effects of engine length. A V20 configuration created a crankshaft nearly 12 feet long. That length introduced torsional dynamics, bearing loads, and structural stresses that couldn't be scaled linearly from the proven V16 platform. EMD proceeded anyway. The competitive pressure was too great. Railroads wanted 3,600 horsepower, and EMD would deliver it. The SD45 entered production in 1965, and initial orders flooded in. It appeared to be a triumph of American diesel engineering. The 2645E3 engine was physically imposing. At roughly 18 feet long, 12 feet wide, and 9 feet tall, it filled the SD45's car body completely. The crankcase was a single-piece casting that had to be machined with extreme precision. Any misalignment during manufacturing would create bearing problems immediately. The crankshaft itself presented unique engineering challenges. In a V16 engine, the crankshaft runs approximately 9 feet. The V20 extended this to nearly 12 feet. That additional length increased torsional compliance, meaning the shaft could twist slightly under load. While all crankshafts experienced torsional oscillation, the V20's length amplified certain harmonic frequencies. EMD installed 2 vibration dampers instead of 1, positioned at each end of the crankshaft. These dampers used a viscous fluid coupling to absorb oscillations. Under normal operation, they worked adequately, but at specific throttle positions, particularly in the mid-range notches where resonance could develop, the dampers struggled to fully control the harmonics. The firing order was carefully designed to balance forces, but with 20 cylinders, the intervals between power strokes became extremely short. At 900 RPM, the crankshaft experienced a power impulse every 0.0033 seconds. This rapid succession of impulses created a near-continuous stress wave traveling through the crankshaft. Main bearing design became critical. The SD45 used 10 main bearings supporting the crankshaft. Each bearing consisted of precision, steel-backed shells with a babbitt lining. Under ideal conditions, a hydrodynamic oil film separated the bearing from the crankshaft journal, but the side loads from 20 connecting rods created eccentric forces that pushed against this oil film. If oil pressure dropped or contamination occurred, metal-to-metal contact could begin, leading to rapid wear. The lubrication system had to supply oil to 10 main bearings, 20 connecting rod bearings, and all valve train components. Total oil capacity was 475 gallons. Oil galleries ran the length of the engine block, and maintaining consistent pressure throughout this extended system required careful balancing. Cold starts were particularly demanding because viscous oil had to reach all bearing surfaces quickly. Turbocharging on the SD45 used EMD's mechanically assisted system. At low throttle positions, the turbocharger was driven mechanically through gearing from the engine. As exhaust gas flow increased, the turbocharger transitioned to exhaust-driven operation. This system reduced turbo lag and improved low-speed performance. However, the V20's displacement and power output required sustained boost pressures that pushed the turbocharger toward its thermal limits. Turbine inlet temperatures ran high, particularly during sustained mountain grades. While the turbocharger was rated for this duty, the margin for error was smaller than in the SD40. Cooling presented another challenge. The SD45 generated approximately 3,600 horsepower at the crankshaft, but only delivered about 3,000 horsepower to the wheels, after accounting for alternator efficiency and auxiliary loads. The difference, roughly 600 horsepower, became waste heat. Additionally, the engine itself rejected enormous amounts of heat through the cooling system. The radiator section occupied the rear third of the locomotive. Dual cooling fans, each driven electrically, pulled air through the radiator cores. At high ambient temperatures or during sustained heavy throttle operation, the cooling system operated near capacity. If radiator fins became fouled with debris or if fan motors degraded, overheat conditions could develop quickly. Fuel consumption was inherently higher than the SD40. While both engines used the same brake-specific fuel consumption rate, the SD45's greater displacement and power output meant it burned more fuel per hour of operation. At full throttle, an SD45 consumed approximately 210 gallons per hour, compared to the SD40's 165 gallons per hour. Over a year of operation, this difference added up significantly. The engineering challenges of the V20 weren't immediately apparent. Early SD45s performed well in testing and initial service. But as units accumulated mileage and operated across diverse territories, patterns of failure began to emerge. Engine block flexing was perhaps the most insidious problem. The V20's block, while heavily ribbed and reinforced, was simply too long to remain perfectly rigid under the cyclical loads of combustion. At 900 RPM with each cylinder firing, the block experienced millions of stress cycles. Over time, this created very slight twisting motions along the block's length. These flexing motions, though measured in thousandths of an inch, had cascading effects. Cylinder liners, which were pressed into the block, could shift slightly. This created uneven seating and allowed combustion gases to escape past head gaskets. In severe cases, cracks could initiate at stress concentration points in the block casting. Railroad shop forces began reporting head gasket failures at intervals shorter than expected. While gasket failures occur in any engine, The SD45 showed a pattern of failures concentrated in the center cylinders, where flexing was greatest. Retorquing cylinder heads became a regular maintenance item. Crankshaft vibration proved more difficult to diagnose because it was load-dependent. At certain throttle positions, typically notch 5 or 6, harmonic resonances would develop. The crankshaft would oscillate torsionally at a frequency that the dampers couldn't fully suppress. This created uneven loading on main bearings and connecting rod bearings. Bearing wear accelerated under these conditions. Shops began seeing main bearing shells with evidence of excessive wear patterns at mileages lower than the V16 engines exhibited. Some units developed audible knocking sounds, indicating bearing clearances had opened up. In extreme cases, bearings could fail catastrophically, requiring complete engine removal and rebuilding. The longer crankshaft also created a phenomenon called critical speed. At certain RPM ranges, the crankshaft's natural frequency of torsional oscillation would align with the firing frequency. When this occurred, oscillations amplified rather than damped out. EMD had calculated these critical speeds and designed the operating range to avoid them, but variations in manufacturing tolerances and bearing wear could shift these frequencies into the operational range. Turbocharger reliability became a concern on units operating in demanding service. The combination of high boost pressure, elevated turbine inlet temperatures, and sustained operation created conditions where turbocharger bearings degraded faster than expected. Some railroads reported turbocharger replacements at intervals of less than 2 years on hard-worked units. Turbocharger failure modes included bearing seizure, turbine blade erosion from particulates in the exhaust, and compressor surge during rapid throttle changes. A failed turbocharger could ingest debris into the engine's intake or allow oil to be drawn into the combustion chambers, causing further damage. Fuel consumption became a major operational concern as diesel prices increased in the 1970s. When fuel cost 40 cents per gallon in 1973, the SD45's higher consumption was an annoyance. When prices hit $1 per gallon by 1980, it became a financial liability. Railroad accounting departments calculated that an SD45 cost substantially more per ton mile to operate than an SD42. Heat management issues appeared most dramatically on Western railroads. Southern Pacific operated SD45s over Donner Pass and through the Tehachapi Mountains. Long, sustained grades at high throttle pushed cooling systems to their limits. On hot summer days with ambient temperatures exceeding 100 degrees Fahrenheit, SD45s would occasionally overheat and require throttle reduction or shutdown. Similar issues occurred on Santa Fe's Raton Pass and on Burlington Northern's Montana subdivisions. The SD45 could pull the trains, but it struggled to manage the heat generated in the process. Crews learned to monitor temperature gauges carefully and would sometimes request a helper locomotive not for power, but for thermal relief. The combination of these problems created a reliability profile that railroads found increasingly unacceptable. While many individual SD45s ran reliably for years, the fleet as a whole showed higher maintenance costs and more frequent failures than the SD45 fleet. As a business proposition, the extra 600 horsepower didn't justify the additional operational expense. Railroad crews had mixed opinions about the SD45. Engineers appreciated the unit's strong acceleration and high-speed pulling ability. The 3,600 horsepower output meant that a 3-unit consist could handle trains that might require 4 SD40s. On fast intermodal trains, the SD45 excelled, maintaining schedule even with heavy loads. The distinctive sound of the V20 engine became legendary. The rapid firing sequence created a deep, urgent rumble that rail fans could identify instantly. At full throttle, the turbocharger added a rising scream that no other locomotive matched. For many engineers, the SD45 was an exciting machine to operate. However, operating departments also noted frustrations. Overheating incidents disrupted schedules. Units pulled from service for maintenance created power shortages. Fuel consumption reports showed costs mounting. As the 1970s progressed and fuel prices rose, dispatchers began preferring SD42s for assignments where either unit could suffice. Shop mechanics developed a different perspective. Maintenance procedures for the V20 were more time-consuming than for the V16. The longer engine meant more difficult access to center cylinders. Crankshaft removal and installation required specialized fixtures and careful alignment procedures. Turbocharger replacements, while not extremely difficult, occurred more frequently than on SD40s. Parts availability became an issue as the SD45 fleet aged. The V20 engine used unique components, longer crankshafts, different bearing shells, specialized dampers. These parts couldn't be shared with the SD40 fleet, creating inventory complications. Railroads had to stock separate parts inventories, specifically for SD45 maintenance. Different railroads experienced varying results based on their operating territories. Southern Pacific's experience was particularly instructive. They purchased 355 SD45s, the largest fleet of any railroad. SP operated them extensively on mountain grades, where sustained high throttle operation was common. They encountered more mechanical problems than other roads and became increasingly dissatisfied with the design. Santa Fe, by contrast, used their SD45 fleet primarily on fast, priority trains across relatively flat territory. Their units ran at high speeds but with less sustained high throttle operation. Santa Fe's experience was more positive, though they still noted higher maintenance requirements than their SD42 fleet. Burlington Northern inherited SD45s from multiple predecessor roads and operated them widely across their system. Their maintenance records showed considerable variability. Some units were reliable performers, others became chronic shoppers. BN eventually concentrated their SD45 fleet on specific routes where high horsepower was essential, and shorter distances minimized operating costs. Norfolk and Western, notably, never purchased SD45s. N&W had a strong mechanical engineering culture and thoroughly evaluated new locomotive designs before purchasing. Their analysis concluded that the V20 design carried too much mechanical risk. They purchased SD42s instead and avoided the problems other roads experienced. Statistical reliability data from the 1970s showed the SD45 required approximately 15 to 20% more maintenance hours per mile than the SD40-2. Fuel consumption per ton-mile was roughly 25% higher. When these factors were combined with higher parts costs, the total cost of ownership significantly exceeded the SD40-2. By the late 1970s, railroads faced a choice: continue operating aging SD45 fleets with rising costs, or invest in rebuilding or replacing them. The answer varied by railroad, but a clear pattern emerged. The SD45, despite its impressive specifications, was not economically sustainable in its original form. EMD recognized the SD45's problems and introduced the SD45-2 in 1972. This updated design incorporated lessons learned from 5 years of SD45 operation. The frame was reinforced with thicker sections to reduce flexing. Cooling capacity was increased. Electrical systems were upgraded to the -2 standard. Critically, the SD45-2 retained the V20 engine. EMD believed the problems could be managed through improved supporting systems rather than abandoning the 20-cylinder concept. Only 136 SD45-2s were built before production ended in 1974. Railroads simply weren't interested. The extra horsepower didn't justify the continued complexity and cost. As existing SD45 fleets aged through the 1980s, railroads initiated extensive rebuild programs. These programs took various approaches, but all aimed to extend locomotive life while addressing the V20's inherent problems. Santa Fe's SD45-2 rebuild program modernized electrical systems and updated control electronics. They retained the V20 engine, but implemented improved maintenance procedures to address known failure modes. These units, designated SD45-2B, continued in service through the 1990s. Southern Pacific took a different approach. After years of frustration with V20 reliability, SP began converting SD45s to SD42 configuration. The V20 engine was removed entirely and replaced with a 16-cylinder 645 E3B engine. This conversion, designated SD40-SEM2, created essentially a new SD40i2 using the SD45's frame and trucks. The logic was compelling. The SD45's longer frame and 6-axle trucks were excellent. The engine was the problem. By swapping to the proven VE16, SP created reliable locomotives that retained the SD45's excellent tracking and tractive effort characteristics while eliminating the maintenance headaches. Other railroads followed similar paths. Burlington Northern converted many SD45s to SD42 configuration. The conversion process involved removing the V20, cutting and reinforcing the frame as needed, installing the V16 engine, and updating all associated systems. The resulting locomotives were designated SD42 since they were functionally identical to production SD42s. Some railroads chose less extensive rebuilds, focusing on extending life rather than re-engineering. These programs updated electrical components, replaced worn cooling systems, and performed heavy overhauls on the V20 engine itself. Units emerging from these programs, sometimes designated SD45-3 or similar, continued operating with the original engine but with improved reliability. The economics of these rebuild programs reflected the fundamental issue with the SD45 design. Converting an SD45 to SD42 configuration cost several $100,000 in the 1980s. Railroads judged this investment worthwhile because it transformed a maintenance-intensive locomotive into a reliable workhorse that could operate another 20 years. A small number of SD45s survived into the 21st century in original or lightly modified form. Museums preserved examples for their historical significance. Tourist railroads operated a few units, where the SD45's impressive sound and appearance attracted riders, but the vast majority were rebuilt, converted, or scrapped. The SD45's legacy shaped locomotive procurement for decades afterward. Railroads became skeptical of high-horsepower experiments that pushed mechanical limits. When EMD introduced the SD70 series in 1992, offering 4,000 horsepower, they did so using a completely new engine design, the 710G3B, rather than trying to scale up the 645 further. The lessons of the SD45 were not forgotten. The SD45 wasn't a failure. It was an experiment conducted at full scale by American railroads, and like many experiments, it revealed truths that weren't fully understood beforehand. The V20 engine demonstrated that mechanical engineering involves complex trade-offs between power, reliability, and cost that can't be wished away by marketing departments or competitive pressures. The fundamental lesson was about scaling limits. An engine design can't simply be stretched indefinitely. The V20 encountered problems rooted in physics, harmonics, thermal stress, and structural dynamics that became unmanageable at that configuration. These weren't manufacturing defects or quality issues. They were inherent to the design. This lesson influenced how locomotive manufacturers approached future high-horsepower designs. Rather than adding cylinders, they developed more advanced turbocharging, improved fuel injection, and eventually moved to electronic engine controls. The path to higher power led through technology, not simply more displacement. For rail fans and historians, the SD45 remains iconic. The sight of an SD45 accelerating through a curve, the sound of 20 cylinders at full throttle, and the sheer presence of these machines created memories that endure. Thousands of rail fans grew up trackside in the late 1960s and 1970s when SD45s dominated main lines. That era is gone, but the fascination remains. The few surviving SD45s serve as tangible connections to that period. Museum locomotives preserve the V20 for future generations. The engineering decisions, both successful and problematic, are there in steel and iron for anyone willing to look closely and understand. The SD45 showed that power alone isn't enough. Reliability matters, fuel economy matters, maintenance costs matter. Railroading is a business, and locomotives are tools that must deliver value over decades of service. The SD45 delivered impressive performance, but at a cost that ultimately proved unsustainable. Yet, even in its flaws, the SD45 represents something valuable: the willingness to push boundaries, to try new approaches, and to learn from the results. American railroading advanced through exactly this kind of experimentation. Some experiments succeed completely, others succeed partially, a few fail. The SD45 falls somewhere in the middle, a machine that achieved its performance goals but revealed limits in the process. For the engineers who designed it, the shop forces who maintained it, and the crews who operated it, the SD45 was a chapter in their professional lives that taught important lessons. For railroads, it was a capital investment that reshaped procurement strategies. And for those of us who study railroad history, it's a reminder that technology advances through trial and error, not just through theory. The deep rumble of a V20 at idle, the turbo scream at full throttle, the sight of an SD45 leading a heavy manifest through mountain territory. These are memories preserved in photographs, recordings, and the minds of those who experienced them. The SD45 era has passed, but its legacy continues in how we understand locomotive engineering, railroad operations, and the complex relationship between power and reliability that defines mechanical design. That legacy is worth preserving and understanding, not because the SD45 was perfect, but because the lessons it taught continue to matter. Engineering isn't about achieving theoretical maximums. It's about finding sustainable solutions that balance performance, reliability, and economics. The SD45 tested those boundaries and, in doing so, defined them more clearly for everyone who followed.